Hi, welcome to Tetryonics. In this crucial lecture, we'll be building on the previous lectures covering the differentiation of 2D mass from 3D matter and the geometrics of EM fields to describe how applied forces can be converted into energies of motion within secondary fields attached to these particles. We'll cover vector forces, linear momentum, how changing linear momentum and acceleration is stored as kinetic energy and magnetic moments within these secondary KEM fields, and how the addition of energy via applied forces or changing motion of these particles brings about wavelength contractions. That's so important to relativity theory, but in this case the Lorentz contractions are shown to be a geometric change. So starting off with the very first principle, you'll see that, as we've discussed in previous lectures, that energy itself has an equilateral form, and that's described by omega. So where you see omega or here omega geometries within the work I describe, you know immediately I'm discussing the equilateral geometry, or the quantized angular momentum of a field of energy, Planck's constant if you like. These quantum coins, have positive and negative charge faces. They have electric and magnetic components and square root linear components, linear momentum versus angular momenta. They combine together in a number of ways to form a self-similar equilateral field of energy. And in this case, as you can see in this illustration here, the equilateral geometry, the omega geometry, comes together in such a way that when you look at it in a quantized fashion, odd number W bosons, odd number charges, combine to make the familiar squared numbers of the overall equilateral EM field. There's obviously an electric component and a magnetic dipole moment within all of these quanta and within the overall scalar field itself of energy. In fact, the quanta that come together in the summation of odd numbers, or W bosons, to form scalar energies, squared numbers, does so in a way that it forms a normal distribution in every case. This normal distribution starts at 1, continues through in integer steps 1, 2, 3, 4, etc., to the mean, the peak amplitude of the EM field, the square root linear momentum, and then decreases back down to 1. Again, all in integer steps. It's this distribution that we'll see later that creates and brings about charged EM fields, but which modern physics presently describes as either a spin, a curl, or a flux at the quantum level. We now know that wherever we see spin, curl, or flux at the quantum level, we're dealing with omega, and Tetryonics represents it in one of two ways, either as a scalar equilateral geometry, as shown on the left here, pi radians, or as an inductive flux or a inductive rotation, a charge either clockwise or anti-clockwise, positive or negative. But it's the arrangement of these positive and negative quanta asymmetrically within the symmetric equilateral triangle, or the EM field, that brings about all the properties that we associate with particles in motion. And we'll go on to discuss this in greater and greater detail in the course of this one lecture. Obviously, because charges are symmetrical at the base quantum level, the 0 point fields, the Planck quantum coins form the basis of all that we can do and all that we can build. This is why it's crucial to build the models, to familiarize your brain with exactly what can and can't be done using these geometries, because they dictate the rules of what mathematics is correct and what's possible at this level. We can use, just quickly touching on the previous lecture, we showed that how 0-point fields of plus or minus charge can come together one of three ways to form electrostatic positive charges or electrostatic negative charges, or neutral electromagnetic fields. Obviously, in the case of electrostatic charges, there's no discernible magnetic moment, but in the case of an electromagnetic field, there is a magnetic moment that can be measured and sensed. The reason why we can't sense the magnetic poles or magnetic fields within electrostatic fields is because they combine north-south to more or less, in lack of a better word, to neutralize each other. We normally sense magnetic poles in particles or in fields by bringing a external magnetic pole close to the particle or field, engaging its response to that pole. If, for example, where the highlight is now, if that was a south pole coming in, the particle or the field would react to it by repelling up against it and creating a force, a repulsive force. If it were the north pole being brought in to measure the field or the particle, there would be an attraction between the north pole, external north pole, and the inherent south pole. So there would be an attractive force. In the case of electrostatic fields, you can't get that push or pull reaction, because as you bring either the external north or south pole in close, it is both, in the case of an external north, attracted to the south and repelled by the north at the same time. So the push-pull is equalized or neutralized by the fact that there are two opposite fields reacting to the external pole that's being brought in. So measurement of electrostatic fields normally results in no measurement of a magnetic field, whereas electromagnetic fields, formed by opposite electric charges coming together, will result in a magnetic moment that creates push and pull reactions. We can model these using tetrayonics, obviously, as 0-point fields, and explain the strength of the electric to the magnetic, how the electric changes in line with the magnetic as you move your sensor down. For example, it starts at at 0 field, begins as an electric as the sensor moves down, or as the field interacts with the sensor. Either direction makes no difference. There's no frame of reference that's particular. What's important is the changing geometry, because as we move through, the electric field rises to a peak amplitude and then begins to decrease. As it begins to decrease from its peak amplitude, the magnetic dipole, north and south, begin to rise. And as the electric field tapers right down to a minimum, the magnetic dipole is at its maximum. And then that would obviously repeat. If we were falling down through this photon or EM field, we would reach a point of minimum, and then it would begin to rise in the negative as opposed to the positive earlier. And the magnetic moment would decrease as the electric field rises. So it's the geometry that's creating this changing electric field amplitude with respect to each other. It's not a case of two waves superpositioned or two different aspects or two different force carriers. It is one and the same geometry that's giving rise to it. And we can use this geometric arrangement of 0-point Planck quanta to give us electrostatic and electromagnetic fields, as well as explaining all the split laws or the different laws that exist at present within electrical engineering. Lorentz's force, Lenz's force, all the right and left hand rules, conventional current, electron flow, all these things can be explained using Tetryonic equilateral triangle of EM fields. So we'll go on and we'll explain it. The only other thing I'll add right here is that, as you can see in the bottom 4 triangles, the positive EM field can also be drawn shorthand as the KEM field. So in the case of a positive charge, a spherical point charge, which we know don't exist, but we can shorthand them as that, you can see the positive Q for the charge with its inductive fluxes for the inertial mass of that particle, and you can see that it gives rise to kinetic energies as well as a magnetic moment, north-south. The opposite charge particle, a negative, say instead of a positron we have an electron, would be a negative charge particle with the opposite spin curl flux for its inertial masses that make up that particle, and the exact opposite resultant kinetic EM field for the same direction. So for positive and negative charges moving in the same direction, the KEM field that's created of kinetic energies and magnetic moments is the opposite. It still has KEM fields pointing in the same direction, but the magnetic dipole has changed, and it's exactly in line with what we've previously called 0-point fields or EM fields, Planck coins. It's the same geometry, except in this case the particle is a spherical particle in the center, and the KEM field is external or added to that particle only when that particle's in motion. What's significant about that? As you can see here, there's several things that are significant about equilateral geometry, and again, this is why it's important to do the modeling. Print out this page, for example, flip it around, play with it as I describe in the illustration, and become familiar with exactly what happens when you mirror or rotate or tile these Planck coins, because it's not at all intuitive to what you initially think. For example, when you tile up in the top right hand corner positive and negative charges within an EM field, and that's all we're saying in that center illustration, is that there is a field made up of equilateral triangles, which in turns creates an equilateral field. That field will have a charge. Wherever you see an equilateral triangle of quanta, you know it is charged, because it is made up of odd-numbered W bosons and sums up to a squared number. So you know W bosons are charges, equilateral geometries are squared scalar fields. But you know that when you go to build these fields using plus and minus charges, that you end up with an asymmetry within the equilateral triangle. The equilateral triangle itself has equal 60-degree angles, hence its name, equal length sides. It's perfectly symmetrical about its axes of division. You mirror reflect that, or you rotate that, you end up with an exact copy. However, when you fill those equilateral tiles with plus and minus charges, you find that you always end up with either a excess of positive or an excess of negative charges within that field. The distribution that we mentioned before, 1 to the peak amplitude back down to 1, the bell curve, results in either a positive or negative charge, unless the only way to end up with an equal charge would be to have 2 triangles back to back, a photon, in which case it would no longer obviously be an equilateral triangle, but a diamond, a rhombic shape. So it's the equilateral, or more importantly, it's the distribution of Planck coins within the equilateral geometry of any field, or in that fact within the faces of any matter particle, that determines its net charge. So another way of looking at that is to say that when we measure a charge on a particle, that charge that we measure is telling us something about the shape of the particle. It's something that's never really been associated before. We know that electrons have a minus one charge, and protons have a plus one, and we know that differentiates them from the two, but equally the positron has a plus one charge and the anti-proton has a minus one charge. So even though it hints at some sort of information, it's not the full picture. Tetryonics gives us that full picture, and I'll discuss that when we describe matter topologies. But suffice to say here that the geometry determines the charge. The geometry of the mass energy will always determine the charge of both a field, or a 2D field, or a 3D particle. So it's an important factor. And until you sit down and cut out these shapes and see how they come together and what charges are created, is something that's easily missed. In fact, 400 years of mathematics hasn't stumbled upon this fact. And it goes further than just describing matter topologies. It actually describes why we are present in a matter universe, not an antimatter one. Additionally, reflections or mirroring around any axis of an equilateral triangle does not give you the same charge. If you reflect on the longitudinal axis or the lateral axis, x versus y, of a positive charge, you end up with a negative charge. Try it. Cut out the picture, flip it over. When you look through the picture, holding it up to light, or if you use it in a computer program as I do, you end up with exactly what you've got there. The mirror reflection of a positive charge is a negative, and vice versa. The mirror reflection of a negative charge is a positive. This does not carry through to rotation. You can rotate any charge about a point, about any axis, and you still have the same charge. Doesn't matter how you rotate that positive charge or a negative charge, you always maintain that charge. So here's where we're starting to hint at some of the technical terms that you'll see in relativity about Lorentz transformations and corrections, where you're changing from one side of a page to another side of the page, or you're changing it from one coordinate system to another. These are just complex wordings trying to mathematically describe what we've just shown here, reflections. And we know, of course, in the case of coordinate transformations, which is just looking at this from the other side of the page, that the opposite side, looking through this page at the positive, if we were to view it from the other side, the flux would be going the opposite direction, and they would see a negative. It's an inherent feature of Planck coins. The opposite side of the coin is the opposite charge. And these opposite charges of all these equilateral coins coming together create EM fields, create bosons. Well, they are bosons, but create stronger charge bosons, create photons, EM fields, and even matter itself. So the important thing here, and it's highlighted over and over in quantum mechanics, is that we can either describe the omega via the equilateral geometry or via this faded out spin curl flux, this rotation, inductive loop. But in any case, how we reflect, rotate, or arrange these Planck quanta very much determines what physics comes back out of it. And this is why you'll often see me quote, if maths is the language of physics or of science, geometry is its grammar. because there's a lot of mathematics that goes into describing these three simple things, and they're described over and over. Unfortunately, without the geometry, many assumptions are drawn from that mathematics that aren't necessarily correct. But once you apply the equilateral geometry of tetrayonics to that math, the erroneous assumptions disappear and you're left with what is possible in nature. And that's the important part. The geometry forms the grammar. It sets the ground rules, the what is allowable and what isn't possible in nature, as opposed to a lot of the assumptions that have crept in, particularly in the last 100 years with the birth of relativity theory. So we've discussed a lot about EM fields in the previous lecture. What we're going to quickly cover here is the fact that within any EM field, which is just an arrangement of plus and minus charges again, when they come together they form a magnetic dipole with an even number of plus and minus charges, but they still have a positive and negative field. And depending how you view that field, things change. But incidentally, if you were to view this negative positive field from the reverse side of the page, you would actually see a positive negative field. But, and here's the key point, despite that, the south-north pole of the magnetic pole would remain the same. So while there's a reflection and an inversion of the charges, depending which side of the page you look through, the magnetic of the electric charges, the magnetic field, the magnetic dipole, does not change. And this is why you can't make models of these things using button magnets, because using the button magnet you do have a north and a south side, not a north-north side. Try it. It doesn't work. You can, however, build them using inductive windings that are short-circuited. Hence the illustrations that I used, the magnetic spin curl flux vectors. We know that the energy within the electric and the magnetic fields are quantized, and that these quantized fields, in addition to having equilateral geometries that produce squared numbers, also have a square root component, which is the vector linear momentum. This is the same as saying mathematically energy equals p squared, linear momentum squared, or E equals mv squared, while p, linear momentum, equals mv. So linear momentum is the square root of the scalar energy. If you again count up the triangles that are in these fields, each equilateral field, the square root, the maximum amplitude of that field, is the height, what's normally termed the height, or the vertical bisector of the field. It's where all the forces are put together electrically, so to speak, to provide a force at the tip, the very apex of the electric field. So where these electric and magnetic fields occur, the magnetic fields balance out, but the electric field always creates a force because of the asymmetry. There's more negative charges in this field than there are positive, and there's more positives in this side than there are negatives. So they both create similar forces equal to each other, but dissimilar interactions. In fact, in the case of opposites, they attract. A positive charge on this side will be attracted in line with the pink arrows, the red arrows, pulling it into the center of the object. But on this side, a positive charge would be repelled away. So it's not appropriate to say it's a law of attraction, as quoted in most texts. It's actually a law of interaction, because a charged particle entering or being found within these fields will react differently depending on its charge and depending on the quantum coins that make up that field. Again, these fields are planar mass energies. You can't see them, smell them, touch them, etc., because they are planar mass energies. Only material objects can be felt, particles. But these still exert a force over a distance. Mass energy is the immaterial medium through which particles can exert forces on other particles. So, looking at an electrostatic particle, defined here as a negative charge point particle, again, we know they're not, but however, it's drawn this way for simplicity and to differentiate it from the field, because it can become confusing in some illustrations. We see a negative charge particle with equal amounts of negative fields radiating out from it. So this negative electrostatic, let's call it an electron for lack of anything better, this electron is sitting here radiating out negative fields. The strength of the fields in both directions is equal, or in any direction is equal. So therefore all the square root linear momentum, the forces radiating out from that particle, are equal, resulting in the particle being stationary. Hence the term electrostatic particle and electrostatic fields. Again, if, as you can see here, the field makeup is similar charged EM fields back to back, resulting in again this balance of north and south dipoles, or north and south fields within the dipoles. So we can't measure the presence of any magnetic field within this particle or within the field, because the push-pull from both to an external magnetic pole being brought in is equal. So it's as if there is no field there, when in fact there is. If we split this, and the most obvious way for it to be split would be either motion in one direction or an imbalance in the number of quanta in one field or the other. So say for example there was less quanta in the bottom field than the top. When you sum up all the positive and negative charges in both fields, you would find that there is more in this top one, therefore the excess would result in a motion, the square root. It's exactly the same as the high school vector sums that you used to do, where you drew two or more vectors and then worked out the resultant vector from those vectors. Except in this case, instead of just pure vectors pointing out from the particle, which indicate the forces applied to the particle, we also include their scalar fields. Why do we do this? Because historically we've only really been concerned about the kinetic energies and the linear momentum of the particle. But when you get into relativity, you also have to explain the observed magnetic moments of the field. And the magnetic moments, we know from the geometry, are in fact equal to the kinetic energy of the particle in motion. So we present the full picture in tetrayonics. And again, the geometry of the kinetic energy, its linear momentum, and the magnetic moment of a particle in any direction of any charge is reflected by the equilateral geometry of the energy itself. So you apply a force, imagine the bottom was not here, the bottom triangle was not here, a force is applied to the base of the particle. That force is converted into kinetic energies, linear momentum, and magnetic moment. The linear momentum points in the direction of the applied force, a vector direction, and the magnetic moment is at right angles or orthogonal to the vector direction of the particle. So it extends out. And these are important. Again, they all stem from the geometry, but they give us different forces all explained within this one geometry. So we can also see, as a final note for this page, that what was classically described as when a particle in motion was mv squared for its energies, or a half mv squared for its kinetic energy, with half the field being kinetic energy, or mass velocity, the square root of the scalar field, being its linear momentum, we now know that the magnetic moment contributes half of the energies, or is half of the energies of that field, equal to the kinetic energy. So we have a full field which we know contains energy. It's all, whether it's magnetic or electric, it's all a form of energy, and it can all be quantized. So instead of a field mv squared, we can equate that again directly to hv squared, which instead of mass velocity squared is now Planck's constant by Compton's frequency, or the number of Planck quanta in the field, gives us a resultant velocity. Mass velocity squared is the energies of the system, or the energies of motion on that particle. So all materials in motion possess a linear momentum, mv. The same particles in motion have kinetic energies, a half mv squared, and those same particles also have a magnetic moment, which is a half mv squared. The kinetic and the magnetic combining together within the KEM field, the kinetic EM field, gives us mv squared, which we now know and can show over and over is in fact equal to Planck's, the squared number of Planck quanta in that field, or the squared number of quantum coins in that field. They're all different measurements: momentum, magnetic moments, kinetic energy, scalar fields, linear motion, applied forces. They're all measurements of the same geometries, different ways of describing what is happening to that particle and what the resultant motions are, what the properties the particle will have when it's in motion, compared to what properties it has when it's stationary. We can look further at these fields. As I said, we have a kinetic energy component. Why don't we sense the charge? Because it is a charged field. It's an equilateral triangle. It must have a charge. It's because charge is determined by the orientation of the magnetic dipole. A north-south dipole makes a positive charge. A south-north makes a negative charge. The energy, be it kinetic or just plain electric field force, in both cases is in fact a neutral energy. It's only the orientation of the magnetic dipoles that tells us whether something is a positive or negative charge. In fact, that's also borne out by the fact that the kinetic energy, a half mv squared, is in fact a diamond shape. We know that it must contain two equilateral triangles. It's a 2 pi geometry. So therefore, it has positive and negative charges. It may be inverted. This is a positive field drawn here. If it was a negative, the negative would be at the top, but it would still have a positive at the bottom. It is a neutral field, a photonic field when viewed from this side. And when Lorentz transformed or looked at from the other side of the page, it would be in this case would be a negative positive. So again, it would still be a antiphoton on the reverse side of this page, remembering that mirroring and translating reverses the charges on quantum coins. So the same thing happens with fields, because fields are made up of photons. Photons are made up of bosons, therefore the bosons, when you flip, will change. So for all intents and purposes, the kinetic energy part is not really there. We can measure it, we can calculate it, and we know it's there because of the observable forces that we measure. we have to account for it. We know that it's a half mv squared. We know mv squared is everything, so the other half must be the magnetic dipole. And the magnetic dipole is what tells us what charge we're dealing with. There is no way of physically measuring the electric field and saying it is a positive or a negative, because positive and negative fields, the photons or even the EM fields themselves, are identical. They both have biradiant linear momentum, pushing forces in both ways. They are both subject to and create the law of interaction in their fields, and they are both neutral because both sides of the coin, positive and negative, cancel out. When we say a negative field, we're referring to a south-north arrangement of the dipole, where positive charges are attracted and negative charges are repelled. If we're talking about a positive charge field, positive charges are repelled and negative charges are drawn in. This is what's happening. The energy itself is neutral, but the dipole is not. And again, in a quick summary, all the formulations for linear momentum, mv being the square root of energy, scalar energy, or scalar or linear momentum squared is equal to the scalar energy. That there's two forms of mass within the scalar field, electric and magnetic, that we can describe the kinetic as a half of those fields, magnetic as the other half, and that we can also model them as inductive loops of spin, curl, flux, are all unified, inherent, and a part of a simple equilateral triangle. The triangle drawn as we see in the center here is the KEM field. When a force is applied to a particle, all the energy that was in that force, that created that force, that was applied to the particle, is converted back into kinetic energies and magnetic moments and vector linear momentum. They're all components of the secondary KEM field. So a particle at rest has no KEM field. It would just be a circular point particle, positive or negative net charge. Only when a force is applied or there is an imbalance in the inherent forces of the particle, inherent mass energies more appropriately of the particle, does motion arise. And when the motion arises, we obviously have a KEM field. It's a completely separate secondary identity. This equilateral field only arises when the particle is in motion. Another way of saying this would be to say, take the particle, strip it of its KEM field, and you have that particle at absolute rest, in fact, at absolute zero. There is no energy of motion, there is no thermal energy, there's no vibratory energy. Stripping away, all those energies are contained in the KEM field. Strip them away, and the particle is at absolute rest, allowing us to calculate the absolute rest mass matter of the particle itself. So that's what this illustration is about. It's simply saying that in the case of either a positive or a negative point charge, we have energies radiating out in any direction. If they are all in balance, we have a case of a electrostatic particle that will, in the case of positive charges, attract negative charges to it while repelling positive charges. And it actually repels the positive charges even more stronger than it attracts negatives, because there are more positive quanta in the EM field pointing outwards than there are negative quanta pointing inwards. And the reverse applies to negative charges. More negatives pointing outwards than there are positives pointing inwards, but still both exist. So positives are attracted to a negative charge, and the negatives are repelled from a negative charge. The law of interaction is brought about by these KEM fields. So where the KEM fields are completely symmetrical, there's a balance. The fields radiate out and form an electrostatic field around the particle to attract or repel other particles, or to change the motion of other particles depending on their masses. When a force is applied, the particle goes from being just the matter topology with its rest mass energies to the particle with its rest mass energies plus the mass energies of its KEM field. There's no matter component to a KEM field. There's only mass energies. And that the amount of mass energies is related to the velocity of the particle. The faster it's moving, the more mass energies it has. Additionally, because we know that the field geometry is fixed, omega divided by c squared equals charge, mass seconds, to go faster you have to put more Planck coins into that field so that there's more energy, more linear momentum pushing it in one direction or the other. But because the field doesn't change size, because it's a measurement of energy per unit of time, E divided by c squared, or energy per light second, because we define everything by the speed of light per unit of time, we know that what must happen is, as we add more Planck coins to this field to make it go faster, or as a result of more force being applied, those triangles must get smaller. As you add more triangles, the triangles themselves must be compressed because the overall geometry is fixed per unit of time. So in doing that, if you're talking the linear momentum component, which is the height of the triangle again, if you measure that length, the physical length of the linear momentum, the wavelength of the triangle, as you add more and more energy, the wavelength must contract. The particle itself does not change, but as the particle moves faster, the mass energy of the KEM field, the blue arrow here, must increase and the wavelength decreases. This is what relativity is trying to describe when it used Lorentz contractions to explain the motion of electrostatic bodies, the foundation of relativity. The foundational tenet of relativity is Lorentz contractions in the direction of motion. So as we increase the velocity, the physical size of these triangles and their associated wavelength decreases as the number of quantum coins increases. But the particle itself, in this case the electron, does not change size. The physical sizes of the matter do not change, and that's against relativity theory. Relativity theory would have you believe that these particles are spherical particles to begin with. We ignore charge distribution because it won't work on a spherical particle, but we say that when it accelerates, these spherical balls get distorted into oblong shapes, and that where the sides stick out a little bit, left and right, transverse to the direction of motion, we have a magnetic moment. This is not the case. What happens is there's no measurable magnetic moment in this electrostatic particle. It's not a spherical shape, as you can see. But when a force is applied, a secondary KEM field is created with its magnetic moment, as you see it there. It also has a kinetic energy component. Half of the scalar field is kinetic energies, and those kinetic energies accelerate particles, attract or repel them within the scalar area of the field. So wherever that field extends out to, anything within it will be attracted or repelled depending on its charge. That's what the electric field is doing. It's accelerating particles. the magnetic field, the magnetic dipole, more appropriately, is pushing particles left and right, depending on, again, the magnetic dipoles in the object that's pushing up against it. We'll see a bit more about that later on. But at no stage does the shape of the particle change. The matter topology is invariant to acceleration. Doesn't matter how fast or how slow it goes, the shape of an electron is exactly the same at all times. What changes, and so is its mass energy content, it weighs exactly the same at rest as it does at the speed of light. What's changed is that more energy at the speed of light is contained in the KEM field than what there is at 0, or even at 1. There would be one triangle versus c squared for moving at the speed of light. And again, the equilateral fields would be identical. But at c squared triangles, that's a huge number, put into that singular size equilateral field would have to be crushed down. As they're compressed, their wavelengths contract. What relativity through E equals mc squared took to be the energy, the wavelength of the energy of the particle in motion, was incorrect. The mass of the matter remains invariant. What changes is the number of mass energy coins in the KEM field. That's why this is an important lecture. This is something that a lot of people that dive into tetrayonics at the wrong end are unaware of, and what confuses them endlessly. They assume that relativity is still in play. It is, but only for the coins or the Planck quanta within the KEM field itself. We'll discuss that later on when we talk about accelerations and spectral lines, etc. Again, this is just a quick slide to show that in the case of electrostatic particles, or any particle, here we have positrons and electrons. Don't worry about their shapes at the moment. Suffice to say that Tetryonics shows us that this shape, this topology, and it's a 2D illustration of a 3D shape, better built and modeled by yourself, but it's the best I could come up with, bar the CAD illustrations that Rennie produced for us. This is the actual shape of an lepton, or a positron in this case, and a electron in that case, and they have exactly the same size but a different charge to a neutrino. Many people assume the neutrino, because it has less mass, it is smaller than the electron and the positron. It is exactly the same size, and this is important in things like neutron stars, etc. It's an inherent part of the geometry. You can't change the size of a scalar field per unit of time. They're all identical. So therefore the particles themselves are identical. The difference between a neutrino and a positron or electron is simply the number of charged faces that make it up. They're all 12 charged faces, plus 12 in the case of positrons, 12 minus faces in the case of electrons. But in the case of neutrinos, you have 6 positive and 6 negative. 2 variations of it, but both cases have an equal number of positive and an equal number of negative charged faces, because they're made up of neutral tetraons, in short, whereas electrons are made up of 3 negative tetraons and positrons are made up of 3 positive tetraons. Again, tetraons don't exist in the standard model, but they are a crucial part of the standard model, or should be, because they are the building blocks of matter, hence the name Tetryonic Theory. It's the tetryon and its charged geometry that builds all the other standard model particles. But these tetrons and their 3D topologies, their shapes, have specific amounts of mass energy within them. And in the case of neutrino, you have 12 Planck quanta making them up. So there's 12 quantum coins making up this particle. But in the case of positrons and electrons, there's actually 1.2 by 10 to the 20. Or, another way of saying it is 12 sides, 12 faces, each with 1 by 10 to the 19 Planck quanta. That's a huge amount of Planck quanta. Thinking about it, obviously, each Planck quanta is mass energy. So squeezing these many Planck quanta into the same region as these results in these particles being heavier than these. So these are more massive, literally. These are the lightest particles, bar tetrons, that you can make. You have neutrinos with 12 coins in them versus positrons and electrons with 1.2 by 10 to the 20. Write out the 20 zeros if you want to get a feel for exactly how big a number that is. But they're all squeezed into exactly the same shape. The other result is, because there's more mass energies in each charged fascia, these are more substantive. Consider these as being made out of paper. And this is made out of the same paper, but it's 1 by 10 to the 19 times as thick as these. It's not. It's literally just all squeezed into the same thing, so the wavelengths are shrunk down. We'll discuss all these features later. But the important point here is, again, there is no difference in the physical size between a neutrino and any other lepton in the family, be it charged or uncharged. They're all identical size particles. When you say the mass energy of a particle increases as it accelerates, you are not talking about the mass content of its matter. You are talking about the increase of mass energy in its KEM field. That's the crucial point. As a force is applied to the particle, again you see the lepton geometries, or topologies I should say. Here, when there is no velocity, when they are at absolute zero, standing still, their matter topology is exactly as you see it there. They have electric fields and magnetic fields making up each charged fascia. The charge of the fascia is determined, and the charge of the particle, inevitably, is determined by the north-south arrangement of the magnetic dipoles on each of these faces. If they're all the same and they all say south-north, 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 then it's an electron. If they go south-north, north-south, south-north, then they are a neutrino. It's the magnetic dipoles that determine whether an external bar magnet will interact with the particle or not. It's the magnetic dipoles that determine whether this is a negative or a positive charge. And it's the number of quanta in each charged fascia that determines the mass of the particle at rest. It also determines, obviously, as we've discussed, how those particles interact with other particles of different or same charges. But once a force is applied, this stationary particle topology remains the same. What changes is there's a vector motion in one direction, depending on which way the scalar field is pointing. And the scalar field points in the direction of the applied force. A force is applied to the rear of this lepton, a KEM field is created, a secondary KEM field is created, and additional mass energies are stored in that field that result in vector direction in one direction. It results in a magnetic moment about the central apex of the particle of either a north-south or a south-north orientation. But that magnetic field propagates out orthogonally, is transverse to the linear momentum. It extends out to the sides, either side of the particle, whereas the vector force, the linear momentum, and the kinetic energy point out towards in the direction of motion. The magnetic dipoles are transverse to it. It's what brought about the original terms longitudinal masses versus transverse masses in physics. The transverse mass is the magnetic moments. The longitudinal masses are the photons, the ones that create linear momentum, linear velocity in a direction. They're all part, and they're all properties of equilateral triangles. The triangles give us the charges. The triangles give us the mass energy. They create the particle topology, its shape. They tell us, they govern how much the particle itself weighs. And they govern which direction it moves when a force is applied, how much kinetic energy it has, how fast it goes, and how strong the magnetic moment is of that particle when it's in motion. It is nothing to do with the spherical particle being distorted, out of shape. It is everything to do with an equilateral triangle. Again, how do they differ? How do electric fields differ from magnetic fields? All governed by, I think I pronounced this hopefully the right way, the Biot-Savart law. It's an interesting quirk that most people think that the electric fields and the magnetic fields propagate out as an inverse squared law. In most cases that's true. The magnetic field and the electric field are indeed inverse square laws. As you measure out a distance, they diminish according to the square of that distance. That's held up and shown to be a result of the equilateral geometry, or dual equilateral geometry, of bosons within photons. Two bosons, two charges within a neutral photon. Photons make up EM fields. You start at a source point, and over time you radiate out a field, which is what this illustration is showing you. 1 second, 2 seconds, etc. You measure out the electric components and the magnetic components, and they're inverse squared. But, and here's the big but, if you measure the magnetic dipole and measure it out, it's actually an inverse cubed law. Won't go into it here. For most intents and purposes, people measure magnetic fields because they bring a magnetic dipole in from one side. They don't compare dipoles to other dipoles. Later on we will, but we don't here. So for most intents and purposes, it's an inverse squared law for magnetic and electric fields. For magnetic dipoles, however, they propagate as an inverse cubed law. You can look it up, you can dig through it. You'll find most of the information on it in electrical engineering texts. Because and there's not a great deal of information even out there, because it's very confusing for modern physics to try and explain why a dipole would propagate at an inverse cubed versus the pole of the same field being an inverse squared. Even the mathematics struggles to try and explain it. I've only ever seen one paper that comes close to giving a proper explanation, or a satisfactory explanation, whereas the equilateral geometry shows exactly why it is. So bundling everything back together for these KEM fields, the kinetic EM fields, we now know that the charge matter topology of a particle describes the shape of the particle. It tells us, the net charge tells us how many charged fascia are in that particle, whether it's a tetration, a dodecahedron, an octahedron, or whether it's an icosahedral topology. It tells us things about the particle because of the sheer number of charged fascia that go into making that particle up. It sets the particle families, if you like. We know that that charge is invariant. We know that the energy content and thus the mass content of the particle is invariant. Once the particle is created, that's its mass, that's its matter topology, and it's all determined by the arrangement and the number of Planck quanta in those charged faces and the interaction that those charged faces have. For example, in the case of leptons, those three tetrons are held apart from each other because their charged faces are all identical. Negative, negative, or positive, positive, negative, negative. However, the arrangement, it pushes them apart because of the law of interaction. It forces, the similar charges are forced apart. But the same arrangements with a slightly different charge result in an attraction as well. So in the case of attraction, the 12 charged faces come together and they form quarks. 12 charged faces become 8 external faces in quarks. Dodecahedrals become octahedrals because of the law of interaction, the law of attraction specifically, whereas the law of interaction and the law of repulsion in the case of leptons keeps those 12 charged faces apart. But when a force is applied to either quarks or leptons or baryons or even tetryons, they don't change shape. The tetrahedral shape of a tetryon that makes up all matter is one of the strongest shapes you can devise. Ask any builder. It is immensely strong. It does not give under most circumstances. So when you accelerate any tetryonic matter, and by that we're describing everything, every form of 3D matter possible, the shape stays exactly as it is. Its energy content stays the same. But what changes, depending on the distribution of the applied forces and the subsequent distribution of the energies of that force, is the particle's motion, its KEM field, its kinetic and EM dipole, and the wavelength of the quanta or the mass energies in that KEM field. So as a particle, material 3D particle accelerates in any direction, the mass energies of its KEM field are corrected. They're contracted or they're expanded depending on the acceleration that the particle is going through. But the particle itself does not change. So the textbooks where you see descriptions of a locomotive moving at near the speed of light and it's 1 inch shorter, or whatever the number may be, are completely incorrect. At the speed of light, a locomotive is exactly the same length as what it is when it's stationary, and it's got nothing to do with the measuring ruler. All the energies of motion that are moving that locomotive at the speed of light, a locomotive is made up of tetryons just like anything else, is stored. All the energies of motion are stored in the KEM field. Those KEM fields create the vector direction of motion, they create the linear momentum, they create its kinetic energies, and they create its magnetic moments. Everything to do with it is all the energies of motion, the kinetic energies, are a result of those secondary KEM fields. So this is why tetrayonics completely undermines special relativity in this sense. The Lorentz contractions are limited to, and transformations are limited to, the KEM fields. They still apply in various senses to the matter topology itself, but those matter topologies and all those features do not change once the particle is created. But when the particle is in motion, those properties do change with respect to the KEM field. I know I've laboured on about it and I've gone on and on, but it's a very, very important thing to wrap your head around. If you've got any problems, by all means, message me and I will explain it again and again in many different ways, but I'm just working through the illustrations we have here. And again, viewed from the top, if this was a negative charge moving this way, you would see a negative charge KEM field, or a negative electric component, but it would also have a positive electric component when viewed from the other side. That's a coordinate transformation. You're simply swapping from being an observer on this side of the field to being an observer from this side of the field. Same as an observer from this side would see the particle travelling towards them, and this one would say it's moving away. They're all frames of reference, and they all give differing results, hence the complexity of the math. One of the most complex aspects you can begin to look at or use relativity for, and where it often fails in satisfactory explanations, is with respect to Amperes Law. Because, as shown here, we apply Tetryonic modelling of particles and KEM fields to Amperes Law, where a current is run between two parallel wires. Now, when a current is run in one direction or the other, depending on whether you're measuring conventional current or electron flow, you will get differing results. And the results are basically about the measurement of the force between the two wires. In this case, the wires are grey. The black point charges are obviously negative point charges, electrons, moving in one direction or the other, depending on the current flow. There also exists, or can be modelled mathematically, electron flow in one direction can be modelled as a conventional flow in the opposite direction, because electrons have a negative charge, protons have a positive charge, therefore an electron moving in one direction can be modelled as protons moving in another. Or equivalently, you can say they're positrons moving in the opposite direction, which is what I've shown here. To work out whether you've got an attractive or repulsive force between these two wires, you would normally use right-hand rules or left-hand rules, depending on conventional or electron flow again. You would use left or right-hand rules, and you would calculate or determine the curl of the electric and the magnetic fields and determine whether they were attractive or repulsive. We do away with all those fields, all the terms of electron versus conventional flow, protons or positrons versus electrons or anti-protons, etc., can all be done away with. And we can simply, and this is one of the exciting things for me, simply draw the KEM field around the particle. In the case of an electron, it has a negative KEM field, south-north, pointing in the direction of motion. So if you reverse the direction of motion of this electron, south-north, to the opposite direction, you would in fact have a north-south, or a reverse field. The field reverses because the equilateral triangle of KEM fields. It's a symmetric field, remember. Change the direction it's pointing, you have to reflect everything else, hence the need to do all the rotations, or at least become familiar with rotation, translations, etc., using equilateral triangles. It's not as straightforward as you first think, but once you get used to it, it's very intuitive. So the electron flow in this direction versus the electron flow in the other direction, you can see that there is a south-north versus south-north. In this case, we have two south poles. So a current flowing in opposite directions in two wires will repel the two wires. If it happened to be a negative charge flowing up this wire and a positive charge flowing down this wire, there would be an attractive force between the two wires because north and south attract. Equally, if there was two positive charges, there would be an attractive force if they were both moving in the same direction. All these combinations of types of charge, conventional versus electron flow, and the charges themselves, positive versus negative, within two wires, can be quickly and easily modeled using KEM fields. No need for right-hand rules. You know immediately if this was replaced by a proton, it would be heavier. It would require more mass energy to accelerate it at the same velocity. Therefore, the mass energies in the KEM field would be contracted more than they are with the electron. But because the electron's lighter, the electron can move faster. So its field is more enhanced by the fact that it's a lighter particle. It accelerates faster than the proton does. The positron, an identical particle, exactly the same mass matter topology. Therefore, it will accelerate at exactly the same rate as the electron. Only thing is, it will accelerate in a different direction to the electron because it's made of different distribution of charges. But again, the KEM field gives us mv squared for the energy that's applied to accelerate the particles. That energy is stored. It's not lost. It's not created or lost. You apply a force. You apply energies to a particle to accelerate it. Those energies are stored in the KEM field. They point in a particular direction, which is the same direction as the applied force, and they create a magnetic moment at right angles to the right angles to the direction and the applied force. Transverse magnetic moment versus longitudinal acceleration. All that's easily explained using Tetryonic geometries. It doesn't matter what shape the particle is. The only difference the shape that the matter topology makes is in its reaction to the surrounding vacuum energies or the medium that it's moving through. The larger the particle, the bigger topologically it is, the more resistance there is of the faces to their motion. And again, the bigger it is, obviously the more mass energy it has, the more inductive loops. Therefore, the more inertial mass there is, the more resistance there is to acceleration, like I said. A positron will accelerate at the same rate as an electron in the opposite direction. But a proton will accelerate slower because it's heavier. It has more mass, more inductive masses within the charged fascias that react to the environments that it's moving through. So we can summarize a lot of things in the final illustration here. We can show that spherical point charges do not exist. You can't make a sphere out of equilateral triangles. Closest you come is an icosahedral, which happens to be an alternate form of a baryon. Protons and neutrons are icosahedrals. They have 36 charge faces and a matter topology of 20 faces. So 16 of the 36 faces are internalized. You'll work all this out when you build the models, and as I talk through the various topologies, which is next up on the list, we'll start talking about the actual shapes of particles. But we know they're no longer spherical. The other problem with spherical particles, which modern theory often just throws in the too hard basket and ignores, is that when you go to distribute an electrical charge around a spherical particle, it distributes evenly. So there's no way, apart from Einstein's suggestion that there's a distortion in the shape of the body, for that electric charge to become a magnetic moment when the particle moves. We know why it does now. It's because when you apply the force, you create a KEM field. You have a stationary particle rest mass matter with charge and a matter topology made up of X number of Planck coins. When you apply a force to it and accelerate it, you suddenly have additional mass energies in the KEM field. You have a magnetic moment, you have kinetic energy and linear momentum, and you have a wavelength contraction in the mass energies of the KEM field as you accelerate the particle, not in the particle itself. These fields are all symmetrical in their field arrangement, in their equilateral field. They're all symmetrical. The quanta that make them up are symmetrical. Planck coins make equilateral fields. Photons make EM fields, bilateral radiation. We can explain both Lorentz contraction and Lorentz transformation. We can explain the mass energy corrections, the additional mass energy when a particle accelerates, and we'll touch on this a little bit further down in QED. We explain what happens when you slow a particle down, i.e. when an electron races into a light bulb filament. It encounters a resistance. As it does, it moves slower. Slower motion, we know that the number of quanta in that KEM field is proportional to the velocity, mv squared. So if you have X number of quanta in that field and you go slower, you must release some of those triangles because it's going slower. As you release, the remaining triangles, Planck coins, expand to the same equilateral field, so their wavelengths increase, and the released photons / bosons radiate out into space as light and heat. Bosons are heat, photons are light. Two bosons make a photon, and it will give specific colors, specific amount of heat for the velocity of the electron moving in the wire. This is what we're talking about down the bottom. You've got a battery connected to a wire. The electron flow is in one direction with its KEM field creating a south-north. That's equivalent to the south-north of a proton moving in the opposite direction. Electron flow versus conventional current flow in a resistive or in a circuit. What's drawn as circular magnetic field lines can easily be reinterpreted and re-explained using KEM fields, and more correctly explained using KEM fields. When it comes to, instead of a straight wire or a resistive load in a circuit, we change that to a coil where the wire itself is no longer straight or a resistive load, a light bulb, glowing light, or a resistor, and we change it to a loop of wire. We then have a situation where, and it's a little bit hard to see here, but you'll see it in the PDFs where you can zoom in, the direction of the electron is changed. The electron has to follow the wire. So in doing so, the point of the apex of the KEM field alters because it's changing direction. That changes the orientation of the electric and magnetic fields within that EM field, within the KEM field. The result, instead of having a magnetic field going up and down around the resistive load as I'm highlighting here, and the particles moving along, the particles move up and down, and the magnetic dipole that was this way now turns sideways. You can think of it as a phase change, if you like. We're swapping the direction of the electric for the magnetic, or vice versa, however you want to describe it. And we're making, by simply winding the wire, we change the direction of the electrons moving in the wire, and we create a strong bar magnet effect, an electromagnet. That's what a solenoid does. You wind the wire, you create an electromagnet, as opposed to a weak electric field around a light bulb glowing, for example. Again, doesn't matter whether you're modeling conventional current flow or electron flow. Both are easily catered for in Tetryonics. And we have a very simple, very elegant way of quickly drawing the electric and magnetic fields of any charged particle moving at any velocity in any direction, because you can wind the coils one of two ways. You can wind them clockwise and anti-clockwise, and winding them in opposite directions will change the orientation of the magnetic field. If you wind this solenoid the opposite direction, at the moment it is clockwise. If you wind it anti-clockwise, you will produce a north where the south is and a south where the north is. No need for tensor calculations, no need for relative velocities, no need for anything complicated, no need for left or right hand rules even. All you need is a simple triangle and knowing which way your battery is connected to the circuit, positive or negative. That's all you need to know. And then Tetryonics takes the rest on from there. Using a simple triangle, you can describe, you can calculate, you can measure, and more importantly, you can explain not only the shape of the particles, and that becomes important later on, as you'll see. You can explain the mass energies of the particle at rest, why electrostatic particles have no magnetic moment when they're at rest, but have one when they're moving, and why neutrinos, for example, are lighter than electrons, yet they're in the same class. You can explain all these things by simply using the equilateral triangle, the Planck quantum coin. And remember, we've invoked nothing flash here. We have simply grabbed a triangle of electromagnetism, the Planck quantum coin, and added many, many, many of them together in only certain ways that the electric and the magnetic fields can go. We've created bosons, which are inherent, photons. We've then created electromagnetic fields and gone on to make particles. But in this lecture, we've explained the electromagnetic field of motion, the KEM field, and that was the important one. The KEM field is distinct from all others in that it's such a vital role that it plays, and yet it's so foreign to how physics is taught at present. It's so intuitive when you come to understand it and see the role it plays and how it explains things. But trying to understand physics, and particular quantum mechanics, from the top-down approach of modern established physics does not give you these insights. You retain spherical particles. You have this view that the mass energies of motion make the particle heavier, when it doesn't. Well, it does, but it doesn't in the sense that it's normally viewed in modern physics. We're not squashing the particles out of shape. We're simply adding another EM field, energies of motion, hence the name KEM fields, to these particles. And that's where, in explaining this, a lot of people who come to look at Tetryonics fall afoul, because they come into it with their academic studies intact. They know they've passed their exams. This explanation is nothing like their explanation. In fact, it undermines special relativity, as I mentioned. But what it also does, in giving us this clear, concise mental roadmap of how particles not only accelerate and are formed and interact, but it flies so contrary to what's been taught that students that come in with a graduate degree assume I'm talking about one thing, when in fact I'm talking about something completely different. You can see that this bears no resemblance to what's taught in the modern textbooks, yet it explains everything that the modern textbooks can't explain. You'll see I often encounter individuals who think they know it all, and that Tetryonics must be wrong on a fundamental level, and yet they are the ones that can't explain where charge comes from firstly, and how charge make particles. They can't explain the basics of the mechanics of nature at the quantum level, yet using their textbooks they're quite willing to try and correct what I've said and what I say and what I have explained. No offense to them, all they are lacking is an explanation like what I've given here. It's as simple as that. Anyone can follow my road path so far from the lectures, first 10 lectures I've done here, and the Tetryonics 101 video that shows you how to put all these triangles together. Anyone can do that, and that's what I intend to do with first grade students through the educational kits. Teach people to build physics, build an understanding of physics, especially quantum mechanics, up from the ground up. Use the triangles to build the models, to understand what's going on like I have. Then they won't run into these quandaries. You'll see there's many other things I can explain, and I will explain. Shapes of particles, acceleration of electrons, for example, how they make spectral lines, even the shape of atoms and DNA, etc. They're all in future lectures. I thank you for the time so far, because this particular lecture is as complex and as important as the differentiation of mass and matter. So again, thank you very much if you've gotten to the end of this point. Any questions, feel free to message me. I'm more than happy to explain as I can any aspect that needs explaining, just so that people have a clear understanding of what it is I am explaining. Thank you again.